Everybody, let's go to 3.6. Very exciting. We're going to learn a few more derivative rules for logarithms. And now for general exponentials beyond just e to the x. Okay, let's get to it. Just a little bit of review of logs, just the absolute essentials, what we need for this discussion. So here's our notation for a logarithm. We might say y equals the log of x with base a is the way you read that. That is interchangeable with the exponential x equals a to the y. Is essentially what, not essentially, but it is what that logarithm represents. Your base is a because you're thinking a raised to this number here would produce that x value, where it all comes from. Okay. Here's the graph for just a general logarithm. It's going to look something like that. If we were to take different bases, that would cause this to curve a little bit differently. Maybe different values of a would cause it to curve upwards a little bit more. Maybe others would cause it to hook, and stay lower. That's the general idea. It always passes through 1 there for a general logarithm on the x-axis, unless you start shifting, of course. And you notice that the domain is only from 0 to infinity. So it never comes back. It never meets the y-axis. It's got an asymptote there. As x goes towards infinity, although it's, it looks like maybe it's tapering off and it's going to level off, but it doesn't. It does keep creeping upwards very, very slowly. So maybe that graph will be helpful. There are 2 special logarithms that have a special notation. We call them the common log, which has a base 10. A common log, you don't actually write the base in there. Notice that's blank. We just say log of x. That means we're talking about a base 10. And there's the natural log, base e, and it's got the notation ln of x for a natural log. And then finally, kind of what this is all about, and the connection with exponentials. An exponential and a log with the same base are inverses. So a couple of examples there. If you saw the log of 2 raised to the x with base 2, thinking, hey, there's an exponential with base 2 inside of a logarithm with base 2, those would be inverses of one another and would simplify to simply x. We could reverse it. We could put the logarithm into the exponent of the exponential. So there they both have base 10. That's our common log. 10 raised to the log of x would cancel out to just be x also. Okay, let's get to some derivatives. Our first question, we're going to start with, what is the derivative for the natural log of x? So because we know the derivative for e to the x, we're going to be able to figure out the derivative for the natural log of x, since natural log has base e. Okay, how's this going to play out? We're going to start with one of those sort of inverse relationships. We know that e raised to the natural log of x would simplify to simply x. So we're going to start with that true statement. We're going to apply a derivative to both sides, like so. Let's take the derivative of both sides with respect to x. Now notice on the left, we're going to think of it like a chain rule. So we're going to think of it as e being raised to the natural log of x, where natural log x is inside the exponent. And on the right side, we just have the derivative of x. Let's see how those derivatives would play out. Well, on the left, because of the chain rule, right? So we take the derivative of the e first, which means we just copy it, e raised to the natural log x. But then we'd be forced to take the derivative of what's inside the exponent, the natural log x. Well, we don't know what that is. That's the whole point of this question, and that's what we're going to figure out. So we're just going to simply write it as times the derivative of d over dx of the natural log of x. That is equal to the derivative of x, which is, of course, just 1. So this is really clever way to figure out the derivative for natural log x, right? We don't know what that is, but that's the whole point. We know everything else, and so we can isolate this by dividing both sides by e raised to the natural log x. Okay, and then we realize, you know what? That simplifies, all along, that's just equal to x. So it was useful to think of it as the e for a while, but now in the end, let's put it back as x, and we figured it out. The derivative for the natural log of x is equal to simply 1 over x. Now, that's kind of surprising, like it's simple, but you would think that the derivative for natural log of x would somehow involve a natural log, but it doesn't. It's just this fraction 1 over x. In that sense, that can make remembering the derivatives for logs a little bit tricky, but because there's this kind of, it doesn't involve natural log, but that's kind of strange. But, we'll be using this quite a bit. So hopefully just with practice, you get the hang of it. Let's look at a couple of examples. Let's look at maybe something like f of x equals x to the third times the natural log of x. Just kind of put it into a context with some other rules. So here we'd have a product rule. We've got x to the third multiplying with the natural log of x. And say, okay, how would that product rule play out? Well, we take the derivative of the x cubed, and we'd be copying the natural log of x at this point. Then we do the opposite, plus x to the third times, and now the derivative of natural log x is 1 over x. And we're looking pretty good. We can simplify that second term nicely as x squared. And so there we go. F prime of x equals 3x squared, natural log x plus x squared. And there we have it, using the derivative for natural log x. Let's take a look at one that involves a chain rule. How about g of x equals the natural log of tangent x? Okay, so chain rules involving natural log tend to give students a difficult time as they're learning this new rule. Here's how we go. So we've got a chain rule, right? The outside is the natural log. The inside, of course, is the tangent x. So how would we do the derivative of the outside, the derivative of the natural log? We go back to the rule. Derivative for natural log x is 1 over x. So whatever appears here inside the natural log, that's what's going to go in our fraction. So if we've got if we've got the natural log of tangent x, then the derivative for the outside is 1 over tangent x. We simply replace the x in our derivative formula with that entire tangent x. Then, of course, we need to multiply by the derivative of tangent x. Well, that is secant squared x. And there we have it. There's our derivative. When it comes to derivatives involving trig, a lot of times you can simplify things nicely. Here, I'm not really sure. One thing that I noticed, 1 over tangent x is cotangent x. So we could simplify that. Do those things if you see them immediately. If not, don't worry about it. We could write that as secant squared x over tangent x and be perfectly happy. Okay. Point, of course, there is the chain rule. All right, let's keep going. Let's do a general logarithm. What is the derivative for the log of x with base a, any base a? You notice where we're going to start. We're going to start with the true statement. This is the change of base formula. If you think back to your algebra days, the log of x with base a is equivalent to the natural log of x over the natural log of a. Again, the change of base formula is that statement right there. Again, we're going to apply a derivative to both sides. Makes sense. We're trying to figure out what the derivative of the left side is. So we're just going to figure out the derivative for the natural log of x over the natural log of a, and we'll have it. Luckily, we just learned what the derivative for natural log x is, so we'll be able to do this. Okay, one thing to notice here, when we're taking the derivative for natural log x over natural log a. The natural log of a, right, the same base that we started with, whatever that is, that a will be a number, and so the natural log of that number is simply another number. That denominator is a constant. So what we can do, since it's constant, we're going to move it out in front of the derivative. It's like a constant multiple, like this. And because it's in the denominator, of course, when it comes out, it's a 1 over natural log a. So that constant can come right out like a constant multiple. And all we need to do and focus on now is the derivative for the natural log of x. Of course, we know what the derivative of natural log x is. It's 1 over x. And so this cleans up really nicely. 1 over natural log a times 1 over x. We can write that as 1 over x times natural log a. So there's the derivative for any general logarithm with any base. It's still 1 over x. So we see that that same theme, but now we'll also multiply by the natural log of a. Let's look at a couple of examples. How about y equals, let's start off real simple here. Y equals the log of x with base 3. How would that work? Well, we're just going to follow our rule and we're just going to copy over, hey, we've got a base 3. So put in a base 3, put in an a equals 3. That's it. Y prime here, 1 over x times the natural log of 3. Just that simple. Just follow our new rule. Okay, let's get a little bit harder. Let's do something with a chain rule. We need to practice these for sure. How about f of x equals the log of x squared plus 1 with base 6? Okay, whenever there's a chain rule, I'd be really, really careful. How are we going to do this? For the derivative of the outside, for the log base 6, we're going to follow our rule. Right? Where we see whatever replaces the x squared plus 1, we're going to put that in where we see x in the formula. So if we have an x squared plus 1 here, this piece, that x, will now be that entire x squared plus 1. Right? Also, our base is 6, so that's the a. The derivative of the outside, 1 over the quantity x squared plus 1 times the natural log of 6. So again, that whole thing goes in where the x would be, and then times the natural log of our base. There's the derivative of the outside. Then, of course, we need to multiply by the derivative of what's in the parentheses, so times 2x. And we might say our final answer, we could just write it all as one fraction, 2x over the quantity x squared plus 1 natural log of 6. Okay, one more thing I want to mention just here in this first video. Let me go over to my paper. We just learned, we kind of summarize these two rules. Derivative natural log x equals 1 over x. And the derivative, the log of x with base a equals 1 over x natural log of a. Now, one of the joys of mathematics and learning math is seeing how these things are connected. The natural log of x, I mean, that is a special case of a log. This is the general case, right? Natural log of x is the log with base e, right? I mean, that's all it means. It's a shorthand notation when you have a base of e. So what if we thought of the derivative in this style and use that rule, right? Would it still work out the way it's supposed to? The derivative, the log of x with base e, it should come out as 1 over x, right? But we're going to use our other rule. So let's see, what would this tell us? 1 over x times the natural log of our base here, which is e. Okay, so that's following this rule. Is that really the same as 1 over x? Yes, because the natural log of e, right? Those have the same base. They can't, that's equal to 1. They're inverses. And so, yep, even if we were to follow this more general rule, we'd still get the same thing, kind of showing this is a special case of the larger rule, but it's the best case, it's the nicest case because of that natural log e that occurs. All right, you guys, let's stop this video here. We'll look at general exponentials next.